So yeah, I don't have many slides. We can go through quite slowly. So if you have questions, raise your hand, because it's not so common physics side of business. It's more of computer related terminologies. So if you're not clear, just ask questions. So yeah, I need to move my side. Okay. First thing first, when you build QMCPACK, you need to enable those GPU features in CMake. So CMake option is -D, the option, then you give a value. It's quite tolerant, so you can say on, off, true, false, 1, 0 as you like. I personally prefer on, off. It's less confusing because true, false, I always type true in the wrong way. So just a quick note. So QMCPACK use two programming models for accelerating on GPUs. One is the OpenMP offload model. The other is the vendor provided model like CUDA, HIP, or SQL, with the vendor provided linear algebra libraries to accelerate the code. Technically, you can individually select those features. There are features that implement as OpenMP. You toggle on enable offload. Or there are features exclusively to CUDA. Then you turn on the enable CUDA to on. There are also features that require both. Then you put both. So I'm listing those features here just to let you know you can individually at build time to select those, but these are more for developers. As a user, you should just toggle on all of them. You select OpenMP offload and one of the vendors. The vendor ones are mutually exclusive, so you can only pick one. So once you do that, yeah, so that is select like what software stack to connect, to use. And in detail, when you run on specific GPUs, our CMake will try a guess like what version of GPUs you have. You have Volta, you have MP or Hopper. So we will try to make a guess, but at the moment, if we fail to guess, we will stop and ask you to input this QMC GPU arcs. Most time, I assume your compute node has only one kind of GPUs, but on machines, if you actually have mixed some nodes, like you have one partition with A GPU, the other partition with B GPU, you can specify them together. The only requirement is it needs to be from the same vendor. We don't support mixing like AMD, NVIDIA. There's no such thing. So just remember, you have those flexibilities. The next thing is C-test. So C-test on CPU only machines running is typically a lot easier, but on GPU there's a bit of caveat, I would say. So you need to pay attention because QMCPACK C-test right now only support running on one GPU. No matter how many threads, how many MPR ranks, it's always talk to the same GPU. So you don't need to really worry about GPU affinity. If your compute node has many GPU, just let the QMCPACK pick one. It doesn't really affect your testing. However, I do notice that a lot of scenarios when you run C-test, you find slow is actually a problem in the CPU because some of the MPI launcher, MPI run, MPI EXE, JS run, S run, whatever, by default cluster all the CPU side business on a single core. So somehow you need to pay attention when you configure your CMake. You need to pass in through those arguments, Paul.
So I think the message here is that running the tests will be definitely run the tests, as you should always do. They'll take a little bit longer to run, most likely, because it only uses one GPU, but it shouldn't be ridiculously slow. If it's ridiculously slow, something is going on here, and it needs looking at like all the CPU threads have ended up on the same core, something like that.
Yeah. So there are three arguments, right? One, the three options pass through via CMake. One is your JS run or S run, that executable. The second is the a number of MPI tasks and MPI processes. What the option name. The third one in the preflags is the one that you're supposed to input your affinity information. I'm giving you an example. If you run QMCPACK as the line, so you have if you have like MPI run, this is your line. You basically take the red part and send it to send to the preflags. So that will propagate to your C-test run, making sure that the CPUs don't cluster on the same one. So that you cannot control it at runtime. You have to configure it when you configure your CMake. But you can down it like once you finish all the building, you just go back and add this -D, this particular flag, and do it once, and it will be settled. And always remember to, when you run C-test, to use -J to maximize the use of CPU cores. Okay. Second is, Jerry mentions about the driver side of changes in all the top level changes in the input. I just want to give you an idea that since we say now we have control of these GPU features at per feature basis, like you can select using GPU or using CPU, or we might even have multiple GPU implementations. So we use this GPU equals something input tag next to the feature and basically allow you to select the specific implementation you want. So the accepted value is usually yes, no is always guaranteed, but like specific ones, CUDA, SQL, OpenP target, CPU ones, it depends on the implementation, may exist or may not exist. Just the rule of thumb is, well, you generally use yes, no in your production, or maybe more in most scenarios, actually, you don't put anything. So it's basically when GPU features are available, it will go, it will set this GPU equal to yes, basically. Then the yes, when it supports multiple GPU implementations, like we may have a CUDA plus OpenP offload implementation. We may also have an OpenP implementation. The yes, GPU yes, the cost level option will hit the best performance when we consider you should use. So most of the time you actually don't need to set anything, but I just let you know, you have the freedom to switch off a feature without rebuilding the whole code, that you can just control it through the input. So here's a figure of typical GPU node we have, GPU compute node we have. I'm using the Aurora node because it's somehow not a perfect, not fully balanced the node structure, simply because the hardware is as it is provided. So on a Aurora node, you have 6 PVC GPUs, and 6 PVC GPUs have 2 GPU, each of them have 2 GPU tiles. So then the recommended way is use each individual tile as a single GPU. So then it has 2 sockets, 2 CPU sockets. Each CPU socket has 52 cores. You find immediately it's not divisible by 3 or 6 or the number of GPUs. So just then in this particular scenario, if you are using GPUs, you have to think how to divide things by the GPU, not by the CPU. And you're okay to let a few CPU cores being idle. So the rule of thumb of selecting how many MPI ranks QMCPACK on a given compute node is 1 rank per NUMA. So when NUMA means non-uniform access. So like if you have left CPU try to access the data on the right side CPU, it's slower than on its own. So this means a NUMA. It's a 2 separate memory domains. Then GPUs again has its own separate domains. So on CPU only machine, you select by NUMA, means you define MPI ranks by sockets. On GPUs, because that's the primary compute device, and you look at how many GPU devices you have and select the number of MPI ranks accordingly. So as I mentioned, PVC tile has 2 per GPU. So overall, the whole node has 12 tiles. So you should definitely set 12 MPI ranks. So it's similar on AMD. So it basically, it has 2 GCDs on per GPU on Frontier node. So you have 4 GPUs, 8 GCDs, and you should use 8 MPI ranks. Okay, here now you have 8 MPI ranks. Now you go back to think, okay, how to divide the CPU resource for the 8 ranks. Here is for 12 ranks. So 58 CPU cores, but you only have 48 cores per socket. So basically you need to make sure you use 48 cores. Each MPI rank use 8 cores and use the first 48 cores on the first socket and use also the first 48 cores on the second socket. It leaves some core idle. So you really need to care about how to put the CPU affinity. Again, you see here we have 12 MPI processes, but if you look at slingshot connection, just read by the figure. I don't remember exactly how many links are there, but just look at the figure. It gives you 8. You find it's also not divisible. Just ignore it because QMCPACK is very light on communication. So it's not usually not the primary things you should care. Just let the runtime, the MPI library figure out which link to pick. So don't try to control it. Okay. Affinity. So I said, now you know how many MPI ranks you have on a node, how many cores you're gonna use, but you still need to tell the MPI that for each MPI process, which resource to pick. So my recommendation is forget our GPU at the moment. First, tackle the CPUs because CPUs kind of predetermine the location of your GPUs. So settle the CPUs first. On that Aurora node, if you're not using GPU, you just set 1 MPI rank per CPU socket. And now since it's divisible because there's only one, you can just use all the 52 threads. But now since we are going to use GPUs, we will use 48 cores, then you need to specify in the MPI exe saying how to bind the MPI process, like each MPI process bind to 8 cores. And you may, in the case of Aurora, you have to actually specify a mask list, say only use those cores. So once you distribute your MPI process and its OpenMP threads on the CPU side, now go back to look at the GPU. So nowadays, most HPC applications run at 1 GPU per MPI rank. That's most applications run at best efficiency. Usually in this way, the MPI launcher comes to a feature allow you to restrict how many GPUs to use per MPI rank. So like -G1 on certain machines. And the certain machines also allow you to say --closest, like to select the closest GPU to the MPI rank. Usually when you have the MPI process affinity to the CPUs, right, then the GPU, the closest GPU is derived from your CPU core locations, and it's always right out of the box. In the worst scenario, if the MPI launcher doesn't support that, I would say just rely on QMCPACK internal mechanism to detect the topology of the GPU node. And it will assign 1 GPU. As we already choose the number of MPI ranks, 1 MPI rank per GPU, or GPU 1 GPU per MPI rank, QMCPACK always find the right ones typically. Just add a note, even on some machines, the GPU ordering may not be as the same as the numerical order. Just pay attention, but I just find it's important. On the other hand, it's not catastrophe. I haven't seen like a terrible performance because of this kind of mistakes. It's light. So always remember to get best QMCPACK performance on those hybrid node architecture. Start with the CPU core affinity, bind the threads, bind the MPI process to the right cores, then settle the GPU selection. Okay, now back as Paul mentioned, he didn't explain the details of crowd. I think I need to get this task done. So QMC algorithm, we know it's called workers. You have those replicas, and the whole worker is called population. So they are kind of physical related concepts. So to maximize efficiency, we introduced the concept of crowds. That is only a way to make the computation efficient. It has nothing to do with the actual physics. It's more of just organization of computation. So the general reason is, as Paul mentioned, you need to have batched worker operation to the GPU to get efficiency. So here with a crowd, with the subdivision of the population, each crowd will be submitted to the GPU as a whole batch. So that will maximize the calculation within this crowd. So and we operate on all the lockstep algorithms. However, between crowds, it's fully independent. So it's fully independent. The reason is, well, we have on Aurora, we have 8 OpenMP threads because of 8 CPU cores. They talk to the same GPU. GPU is there's only one GPU, so it may serve many threads, but it cannot serve them all at the same time. And sometimes this thread, this crowd is working on some CPU business, prepare for a submission of a computation to the GPU. We don't want to leave the GPU idle, so we kind of have an independent crowd may submit work continuously to keep the GPU busy. That's the reason of how using a crowd to maximize the GPU execution. So conceptually, if you think about crowd size 1, you have as many of crowds as the number of workers. That's basically what we have in the CPU code. That's why you figure, Jaren said, when you're using GPU, using CPU only, you run to switch to the batch code. Don't specify anything. You don't need to specify the number of crowds. And as Paul said, you can just ignore this concept existence. But on the other hand, if you think about the whole population as a single crowd, which falls back to the original implementation in our very legacy deleted CUDA code. So basically, this crowd, the introduction of the crowd enables a flexible breakup of the two worlds. So one last thing is, even you have those crowds, there's a debug feature you can turn on to set the crowd serialized workers. So even within a crowd, we can execute the computation one worker at a time. There's no guarantee the implementation is identical because certain calculation is batched. Before you have to do a matrix vector multiplication per worker. Now you do a matrix multiplication. There's no guarantee of a bit by bit numerical in numerical comparison. So just be aware of that, but both supposed to work. Josh?
Is the point of crowds to have asynchronous groups?
Yeah, if you're talking about general concept of asynchronous, yes. So one crowd is fully independent of another crowd when they are doing P by P moves, or actually even doing Hamiltonians, they are one by one independently. Yeah.
Can I add to that? I mean, so this is a good question. And so I'd say actually the main idea is to be able to increase the asynchronicity, right? Because the crowds are sending requests to the GPU independently on their own time scale. And particularly as we start to add, more observables in a calculation and so on, right? That might well help the performance. There's more about this in Ye's paper. And I think possibly my IPAM talk, which is on YouTube, has got a figure showing what's going on. So we do see it gives increased performance already, but we think it's useful flexibility to have in the future as well.
Yeah.
Sorry, but sorry. So in Paul's talk, he showed the slide where you have walkers per rank and you kind of saturate. Is there a similar kind of figure for crowds then?
I will explain that later.
Okay.
Okay.
I can show you later if he doesn't have it.
So this figure is more of if you're interested in the background, like how things are happening on the GPU. So you've seen 4 OpenP threads talking to the same GPU. You will see at different time, each thread is doing different things. Some of them was copy data to the GPU. Some of them are doing computing. So there's a lot of overlapping. That's the intention to maximize using the resource on the GPU, both for computation and for data transfer. So this is by design, we just get those features out of this crowd design. If you're interested for more details from a computer perspective, you can go back to read that high-part paper. Okay, so before talking about performance, I'd like to define a throughput when we say QMC throughput. So throughput in an even broader definition is a workload, the amount of computation over the time execute the computation. So in QMC is generally the number of samples over the amount of time you execute to get those samples. Sometimes in QMCPACK, we write as walkers steps per second, because walkers means the population size. The steps is the total number of steps in this QMC driver's execution. Per second is divided by the time unit. So to be more specific is population size by the steps in the input block and blocks and over the total driver time. So the quick question is, now if I double the node count and double the population size, how does the throughput change? Who will volunteer to answer? Yes, it's the same. So you're not gaining throughput in this way. Actually, no, actually it's not true. No, another answer? Huh? Yeah, it's doubled. But if you think about throughput, because you double, no, the throughput is doubled, but you put double amount of resource, you are not really gaining efficiency. Think about that. Yes, you have twice number of samples at the same time, so you double the throughput. But on the other hand, you don't gain efficiency, right? Because you put double the amount of work counts. Okay, second question is, if I double the steps or blocks, how does the throughput change? From this side. Yeah, it doesn't change because you double the time as well when you double the steps or blocks. Okay, so these are not options for us to improve the efficiency. So when we are talking about GPUs, what we want is maximize efficiency per GPU. So we talk about the throughput per GPU, right? So now go back to the figure Paul have already shown. So this is to measure the throughput per GPU. So the number of workers is the total number of workers per MPI process, which works on that exclusively on that GPU. So what you notice is at the beginning, your worker count is low You double your worker count, you don't double your time. You only increase slightly your time. That you see the shoot up of the GPU throughput. At a certain point, GPU is busy. Now you throw double the amount of workload. Basically, the GPU has to finish the first half, leave and finish, and then put on the second half. The time also doubles. So you no more gain the throughput. That's why eventually it saturates. So usually a measurement, a worker scan figure has this pattern, is it will shoot up and saturate. Eventually it will flat, but I'm expecting the tail is very long. So don't try to get 100% efficiency. It doesn't make sense. You have to think about your time to solution. So usually you get 80%, it's okay. Yeah, you're not losing much. And second is look at those two curves. One curve have only one crowd, the green curve. No, the red curve has only one crowd. So one crowd, yes, in the beginning it runs faster than the 7 crowd. The green line has 7 crowds, the same total workers. So GPU are running the same amount of things, but when you have 7 crowds, each crowd size is smaller. So GPU is less efficient for dealing this. So it takes more time. So with the same amount of workload, takes longer time. That's why a 7 crowd loses in a small worker count range. Now gradually you increase the worker count, GPU gets busy. Well, on the other hand, you have to remember your CPU also gets busy. If you're using only one crowd, you're only dealing everything on the CPU side with one thread. Those gonna be your bottleneck, following the Endar's law. That's why actually at the saturation range, having more crowds is beneficial. On the other hand, you can't throw in, like, if you ask me what's the best number of crowds, my current experience is I don't know, unfortunately. But usually the rule, yeah, try starting with one crowd, like one thread, then you do 2 threads, 3 probably jump, like 4, 8. But furthermore, definitely don't go beyond 16, because I said if you have all the crosstalk in the GPU, it consumes slots on the GPU. GPU doesn't have hardware level, doesn't have that many slots to asynchronously schedule your request. So there's no point of going beyond that. So if you don't want to kind of mess with it, choose 4, 8, kind of just let it go. My personal experience. If you're a bit serious, try to do a scan. That's it. Okay. Yeah, a few more words about these workers per rank versus total workers. Just a reminder, the workers option is no longer accepted. You will get an abort immediately if your input contains this one. Just to remind you, you have to use workers per rank or total workers. If you provide both, you will be checked against with this equation. So most of the time you don't need to specify both, or not most of them. Actually, you don't want to specify both, but we add a sanity check. When you provide both, we will check. If it fails, we'll stop you. If you set one, the other one will be derived. But if you don't set anything, it's actually recommended for the CPU, because by default, the workers per rank is set to the number of crowds. The number of crowds is default to the number of OpenP threads. So you actually have 1 worker per thread. Everything's good. So don't need to set it.
I should add, and this is the long established behavior of the current code, right? So everything is handled for you automatically in this case.
Yes and no. The old code has a weird behavior. if you set worker 1, you see the next input like generating input, you will always set workers 1. Actually, the behavior on CPU and GPU code is different, and it will actually promote to a number to be a multiple of your OpenP threads. It's all behind the scenes, but it's like a black box. You don't have precise control. So the new clean logic in QMCPACK right now is, if you don't set anything, we set a default. If you set a thing, we absolutely respect it. So if you set like a 7, world workers per rank at 7, you have 8 threads, we will only run 7 workers. The logic is simple. If you are bound by the CPU memory or GPU memory, it doesn't make sense to add more and hit the memory wall and stop your run. So we don't evilly add things to the ones you've instructed. Okay. Yeah, so I personally most time just use workers per rank, not instead of the total workers. The reason is workers per rank is related to efficiency, memory capacity. So yeah, that's basically, I recommend just focus more on workers per rank. Yeah, so optimal value is actually quite dependent on the selected features. Both the number of workers, the workers per rank, or the number of crowds, actually. I will mention that at the end. Okay, a bit of memory considerations. The reason we choose 1 MPI process per NUMA is because of those data access patterns. We have data structures shared across the workers, consumed by the workers within the MPI process. One example is the B-spline table. When we try to have fast access, we have GPU resident, make a GPU resident. So yeah, even you think like LCAO, you don't have like a B-spline table, such big memory structure. We still have like molecular orbital coefficients shared across all the workers, and you may want to use a GPU linear algebra library call. To be efficient, it needs to be on the GPU. It's also resident. So we have those things try to be resident, but it doesn't need to be replicated per worker. So to maximum, how to say, minimize the usage of GPU memory without compromising performance, basically. Just a reminder, certain operations like single determinant in the single determinant code, we do by default do the matrix inversion on GPU by default, because I assume most people actually for smaller problems won't hit the memory wall. But if you do hit the memory wall, you can leverage the fallback to the host, like run this feature, do the inversion on the CPU side using a regular laypack. You don't need scratch space on GPU. So that also free up the GPU memory. On the other hand, for sure, we'll maybe slow your code a bit. And even if you do the worker scan, the behavior was, the curve will slightly change. So the optimal one might slightly change, right? So all the GPU performance really kind of depend on the selected feature you are using in your particular simulation. Just keep that in mind. Another one is you can turn off all the distance tables on the GPU, run it on the CPU. You save GPU memory. On the other hand, some of the GPU features will be disabled. So for example, your gesture factor depends on the distance table. If you select the distance table to be on the GPU, your gesture will be on the GPU as well. If you force it to say GPU yes, it will say, no, 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 you can't continue. So that's why, again, the GPU equals something that option most of the time, leave it blank. That's the logic in all the new ways of handling GPU features. Okay, these are performance slides just to tell you that, yeah, GPU accelerates. I don't really think it's any particular surprising, right? So this is on Summit. It has 6 V100 GPUs. It has 2 sockets, Power 9 CPUs, which is quite weak. So the figure actually give you three data set. The reference is the legacy CUDA code we actually have removed because after seeing this result, we are convinced that the batch driver, which is the green bars, is already like around the legacy CUDA code. We can do better in the future, but definitely we're already at the level of legacy CUDA code. And as Paul mentioned, there's all sorts of bad things of the legacy CUDA code, and we just deleted it. The purple bar is the CPU. You see it's just tiny. So it can be like more than a factor of 10 speed up. So this is Polaris. It's so now the rest.
You need to explain what Polaris is because most people won't know.
Okay. Polaris is a Cray machine. Each node has 32 CPU cores, single socket, and 4 A100 GPUs. So now the baseline is the CPU performance. So x86 actually libraries are a bit more efficient and has wider vector support. So the CPU performance is actually better. Even though A100 is faster than V100, but there's only 4. So the speed up is not so significant compared to the the Summit machine. But again, you can see there are speed up both like a maximum you can hit like factor of 8 using mixed precision. But I would say, yeah, you clearly see advantage of running the nickel oxide benchmark of across the board range of problem sizes. So smallest one is only 8 atoms. The largest one is 512. Okay. So this is further boring thing is just let you know QMCPACK scales fine. Strong scaling, weak scaling. That's why I was saying earlier that you don't need to worry about networks. Our demand on the network is very, very light. So basically, you get almost perfect linear scale up, and also for weak scaling, the efficiency drop is quite minimal. Okay. So the last thing, add some reminder for words I want to say. The GPU implementation may not always accelerate. So just to remind you, you may need to think a bit whether your computation is worth being accelerated or not. It has implementation constraints. So if you're telling me I'm doing a single water molecule, I want to use GPUs, I would say probably you should just use the CPU code. It's already good enough. And maybe you should not even need an HPC. You just find a power workstation and problem solved. So I frequently got people ask, oh, QMC is very expensive, but a lot of times for a lot of problems, you don't need a beefy machine. Okay, yeah, so 10 electron, if you have a 1 million determinant, you can gain, because your major cost is doing the 1 million determinant, not related to the 10 electrons, so you can still get accelerated. But if you're doing a 10 electron single determinant B-spline calculation, you won't gain. Even you put like 1,000, 10,000 workers throw into it, we can't make it efficient. Because for GPUs, each minimum concurrent compute unit, you do like 30 to 64 things at a time. You only have 10 electrons. We can't kind of fusing the 10 electron with the next worker 10 electron and fit into the slots. We won't support that kind of execution. So it won't work efficiently anyway. Just stick with your CPU. Yeah. Second is take advantage of runtime control to mix and match GPU usage and maximize code performance. As I've shown, you can run the inversion on the host to save memory. You may like switch off certain features if you, I don't remember there's such case, but it could happen. There's a feature that only works on small number of things. And yeah, when it works on large problems, it go out of memory. Or the algorithm is only efficient for large problem, not for small problem. So you can just use the GPU equal no, yes, to opt in, opt out certain features. to maximize the use of GPU and also the performance. So if you have questions for performance, remember that you can always enable QMCPACK, the timers. Just set this option and you will get a report at the end of your execution. I think also one reminder, so QMCPACK has features to stop calculation on the fly. So even you run, like you want to do a quick run, you don't know how long it runs, and you figure I get enough statistics and I just want to read the timer, you can stop the code on the fly and will finish by itself and you can see the time to have another idea. Yeah, so that's basically what I have. Any questions?
All right, thank you very much, Ye.
Fernando. Big blind spot.
Sorry, this is a little bit off topic, but you are the person to ask this. So you are running about 1,000 workers per GPU and several ranks, several nodes. So you probably have over 20 workers. I wonder why you just don't write a fixed number of workers with a branching scheme that keeps a population constant. That will solve a lot of problems with efficiency, particularly in very large ranks. It's not difficult to implement, and I don't think there will be any problem with population control for that large number of workers.
Yeah, about fixed population, I do have kind of code path prepared. Right now, because in the beginning when I was coding, I need to guarantee that the code, when we switch to the edge, the behavior mostly stay the same, and we don't have sufficient test, or I don't even trust the fixed population implementation in the legacy driver, so I don't have things to compare with. But it's something we definitely valued in terms of both performance and also simplicity in a lot of places of the code handling.
In practice, we have that for a very large run, if people want to push the boundaries of memory, then there is always one node in a very large run that may crash because of lack of memory. And that turns the efficiency of your code to zero very quickly.
Yes, surprising stopping user is bad. It's a shame, I would say.
This was such a good question, Fernando. I was wondering if someone had planted it, but apparently not. I'm seeing denials from Jimmy. So this is on the list to do, right? It's everything you said is true, right? Having a constant worker population will avoid a fluctuation somewhere on a large run, bringing the whole thing down, right? Which is zero efficiency, right? We definitely don't want that. And, you know, to be honest, the reason it's not there right now is just because of the legacy spaghetti, right? People have attempted to put it in the past and not been successful. So once we're up and running, you know, on these machines and so on, there's a lot of balls in the air. This is on the list to do, because in addition to the points you made, I also agree with the points Ye made. It's very appealing in terms of simplicity inside the code and so on as well. And maybe there's even a little bit of extra performance there. So it's on the list. It's just there's a couple of other things ahead of it on the list for us to do first, but it will come. There's a question further back.
Thanks. So I just had two questions. One is just like clarifying when you were saying assigning GPUs to MPI ranks, and it's going to be assigned based on closeness. Is that like memory transfer closeness or?
Interconnect closeness.
Okay.
So if you use like HWLog, you show the topology, it assigns a number to represent the closeness of different CPU, GPUs,
Okay.
and GPU, GPUs as well. So yes, it usually translates to the bandwidth, that the net, the speed.
Okay. Thanks. And the other question is just if I'm being really careful, I think the takeaway is I should do a 2D scan of like walkers per rank, and then the other one would be the crowd size, and just like 2D scan in that.
I would recommend you first do the workers per rank scan on a single MPI, and figure out the number of crowds secondary.
Okay.
Any more questions? Anyone online? I do have a comment, but let's just see if there's anyone else. Okay, so I think it's apparent that this GPU execution is quite complex, right? There's lots of balls in the air, but we're doing the best we can think of to do something reasonable given the complexities of the technology, right? The nodes are getting much more complex, but it is clear, there's going to be an efficient recipe for each machine, right? And we will share that, right? So it's going to become, I think, apparent very quickly what is the best way to run on Aurora, for example, and that will end up in the manual or some documentation somewhere. And so if you're running on a new machine and you have to tackle with this, talk to us and we'll be happy to share, the experiences we have and, provide hopefully a very good initial guess, because there's certainly a lot of complexities if you've not gone through this. And of course, every code running on these machines has to tackle with this as well, but that's the technology we've got to deal with.